So applications of trig functions are really interesting because there's a whole bunch of things in real life that actually follow these what we call sinusoidal curves. By the way, one of the worksheets has like complete the following sinusoidal applications, or use a sinusoidal function to model the situation. And a lot of students think that means they have to use sine. It doesn't. Sinusoidal just means like sine or cosine curve. Okay, so sometimes we call these sinusoidal applications. I'm just calling them trig applications, modeling problems with trig functions, real world problems. But you may see that word, so don't get surprised by that. Anyway, my point is there's a bunch of things in real life that follow them, and one of them is like the tides. Now, the tides aren't a perfect sine or cosine curve, but they're somewhat close. And there are other things that impact the tides, and they're not on a perfect 12-hour cycle, but we're going to just assume it's exactly 12 hours to make it easy. But other things like daylight. So the amount of daylight per day throughout the year forms a sine curve. Okay, and if you could look it up online, and it forms a really nice sine curve, and you can get data. Like you could look up the data yourself and put that data into a spreadsheet or a graphing technology or something, and it'll be a really nice sine curve. Okay, and then there's a few other popular ones that we see. We're not going to look at too many different types, but one of the other types that we will look at is a Ferris wheel. So imagine this is a Ferris wheel, and there's your rider. There's you. You get on at the bottom, okay? And this is going to map your height over time. So the Ferris wheel starts, and you've gone up halfway, and halfway looks like 20. Looks like about 20. I could zoom in a little bit, and we see that it's about 20, okay? And then you go up to the very top, which looks like just over 30, maybe 32, something like that. Okay, I think it's probably 32. So now you're up to the top. And now you're going back down to the bottom, but time is still progressing. So the graph continues going to the right, but goes down to the bottom. And look what happens. You get a very nice sinusoidal curve. Now this one, we've chosen cosine, and you'll find we often use cosine, because often it's nice to have our application starting either at the top or the bottom. That's just natural. If you're doing a Ferris wheel, you're probably going to get on it at the bottom. I haven't seen very many Ferris wheels where you get on at the top and it rotates you down to the bottom, right? You get on at the bottom and it takes you way up high to the top, okay? And you think about things about a Ferris wheel. How long does it take to go all the way around? Well, that's the period of the cosine curve. How high is it? How tall is it? Well, that's the maximum height. And the amplitude, and if you change the maximum height, you're changing the amplitude of the function, right? So the things that are important about a Ferris wheel, this one's faster than this one. Oh, so it doesn't take as long to go all the way around. It has a shorter period. Like you would talk about it with natural language as this one's a faster one, this one's slower, but it's taller. But what you're saying is you're talking about the properties of the trig functions, right? So like that's why when we think about applications, some people might think about word problems as being tricky, but in this case, all we're talking about is the properties of the function. And so what you need to do is you need to think about the particular application that you're doing and connect those properties to the function properties and to the things, the details that you're given about the problem or the things that are going on, right? How high off the ground is the bottom? Because the bottom probably doesn't scrape against the ground. It's lifted off the ground. That's your minimum height. So that minimum height of the Ferris wheel to the maximum height of the Ferris wheel, half of that distance is your amplitude. If you're starting at the bottom, it's got a reflection, so your A value is going to be negative. Like these are the things you want to think about. Okay, so that's the general overview of how we do these applications. But let's do one together. Like I said, this one's one about tides. So the tide off the coast of Durban, South Africa ranges, and these numbers I looked up, they're relatively accurate. That would be at a particular time of the year, because I think tides are sort of different throughout the year, but these were real numbers. Okay, so from about 0.8 feet to 6.4 feet. So that's a pretty big difference. Almost 6 feet difference. Whew. 6 hours later, and repeats this cycle once every 12 hours. So it goes from the min to the max in 6 hours and then repeats in 12 hours. We'll come back and talk more about that. So make a sketch of the relation over a 24-hour period and then determine an equation for this relation. All right, so I'm going to draw in some axes here. So this is going to be height. In feet. This is going to be time in hours. And I'll call height h and time t. In real life, you would be talking about time of day, and I've done this example before about time of day, but that adds a whole level of complexity, and I'm not going to test you on it with time of day, so we're not going to talk about that. But again, if you were doing this next year in university or in a different course in a college program or something like that, you probably would be challenged to talk about time of day. So if the low tide happened at 3 o'clock in the morning, 6 hours later, high tide would be at 9 o'clock in the morning, and like you would have to somehow translate that into your graph, right? And understand the difference between 3:30 is 3.5 hours, not 3.3 hours, that kind of thing. But we're going to skip that. Okay, so for us, it doesn't say make a sketch of the relation over 24 hours. We'll start at a minimum. Okay? Sometimes it'll say starting from the lowest. Or it might say, which is good because some of the questions are actually about that. Or it might say starting from the highest. Okay? So you have to be careful because that will impact the answers. So I'll start from the lowest. The lowest is 0.8 feet, so I don't need a proper scale. I'm just going to come up and put a point here, and I'm going to label it. And I got to get 24 hours into this graph. So 6 hours is about a quarter of that. So I'll go about a quarter. 6 hours later, it goes to the top, and I might as well have my graph using most of the height of the graph as well. So that's 6.4 feet. Okay, and then about the same distance, and I go back to the minimum. And then about the same, and that's 12 hours. Oh, that was better before. And then about the same distance, there's another 6 hours. So now we're at 18 hours, back up to the top. Same distance, another 6 hours, back down to the minimum. And there's your 24. So look, I'm gonna label all these. There's 24 hours. There's 18 hours. There's 12 hours. That's 6 hours. And I'm not even really thinking about how this is trigonometry. I'm just using my common sense. It says 6 hour, it takes, it goes from 0.8 to 6.4 about 6 hours later. So I went 6 hours and went to the top. Then 6 more hours back down to the bottom. 6 more hours back up to the top. Labeled all of those. Now I'll draw it. last point was a little bit far out, but not bad actually. So you can see that was 2 cycles. Repeats every 12 hours. We had to draw 24 hours of it, so that was 2 cycles. If you're going to explore tide pools, you would want to go at low tide. If you're a surfer, you go at high tide, right? That's when the waves are the biggest. That's when you've got the deepest water. So these are things that people who live on coasts and do these things, that they watch for those times of when tide goes in and when tide goes out. So make a sketch. The important part of a sketch is that you've drawn nice axes and drawn them with a ruler, that you have labeled your axes, okay, and that you have labeled the position of those points on the axes. I don't need a scale, like 1, 2, 3, 4, 5. I don't need that. We're just labeling important points, which are going to be for trig, things like the minimum and the maximum. And then every time you draw another point, label it on the horizontal axis as well. That's what's required for a sketch. Does that make sense? B. B says determine an equation for this relation. How do we do that? Remember when I said, when we first started doing equations from graphs, I said, when you're developing an equation, what are you actually doing? What's your actual goal to be able to write the equation? Because that's what you're going to do in this case as well. What do you think, Shamir? The variables A, K, C, and D. Once we get those, we just write them into the equation. Do you want to use sine or cosine? You get to choose. Why would we use sine? You probably think I'm crazy to even ask that question. You're like, it's not a sine curve. It is a sine curve if you start there. But why would you do that? Because then you got to add a phase shift in and figure out when that is. I guess it'd be halfway between 0 and 6, so it'd be at 3. But why would we do that? So why wouldn't we just use cosine and not use a phase shift and have it flipped? Because that looks like a flipped cosine starting at the minimum. That seems to me, and then ignore the phase shift. That seems the easiest thing to me to make this thing work. So that's what we're going to do. So cosine looks like this. Y equals A cos K x minus C plus D. So we have to find A. We have to find K. We have to find C. And we have to find D. And we don't have to do them in that order. We can do it in whatever order we want. What would be? 0. What? D? I don't think D is 0. Something is 0. Huh? So 0.8, but hold on, be careful. Okay, good. So it is shifted up. But D is the 0 line, not just the minimum. It's not a shift of 0.8. So I'm going to come back to D in a minute. There's an easier one. What is? The amplitude? How did you get that? And okay, good. So amplitude is the max minus the min, so 6.4 minus 0.8. What do I have to do to it? Divide by 2. Very good. $2.8. So A is negative 2.8, right? Negative 2.8. We're doing cosine. Cosine starts at max or min. This one starts at min. So no phase shift. So the C is the easy one. That's 0 in this case. There might be cases where you would have to have a phase shift, but most of the applications you're probably going to get away with C being 0. Now I can find D. Now that I have the amplitude, it's going to be a little bit easier to find D. There are two ways of finding D. I can find the middle of the max and the min. So to find the amplitude, I do 6.4 minus 0.8 divided by 2. To find the middle of them, I would do 6.4 plus 0.8 divided by 2. But I think the easier way, does anybody know what the easier way might be? To find the D. So the zero line, I'm just going to eyeball it, is going to be in the middle, right? Whoops. So maybe right there. How do I get it? Con?
Get the minimum and add the amplitude to it.
Yes, very good. Add the amplitude to the minimum or subtract the amplitude from the maximum, right? So 0.8 plus 2.8, whoops. So that gives me 3.6. So we did the minimum plus the amplitude for that. K value. How do we get the K value? How were we doing it before?
24 divided by 18.
Why?
Because originally let's be like 360 or 2 pi
2 pi?
divided by k.
Yes.
And that's like the whole cycle.
Yep.
So in this case, 360 or 2 pi would be the whole cycle.
Good.
This graph.
Okay, so I'm going to stop you right there. That exactly right. We got to use that little formula. You're always going to use that. We're working in radians, so we're going to use 2 pi. But here's the trick. Be careful. We drew 24 hours, but that's 2 cycles. You got to divide by a period length, which is 1 cycle. So how much was 1 full rotation until we repeat? 12 hours. So it's going to be 2 pi divided by 12. Okay? Don't get confused that you drew 2 cycles and think that it's all the way to 24. It's just the 1 cycle to 12. So K is always 2 pi divided by the period, and our period is 12. So our K value is pi by 6. 2 pi by 12 is 1 pi by 6. I got AKCD. I can write the equation. X minus 0 or just X. There it is. I don't need the brackets. I started with square ones because I was thinking I was going to do big brackets and then round brackets, and then I remembered that, well, C is 0, so I don't actually need round brackets. So you could have obviously just used round brackets. But if some people like having 2 sets of brackets, if they've got the inside one with a phase shift, they just find it cleaner and, more clear. More and more moving into the next unit on trig, we will not be writing those brackets all the time. So it is good to get used to them. But that I was doing them just in case there are people who like to see the brackets. Okay? Everybody good with that? So it's not too bad, but you have to identify the important points, the important details of the application. Where's the max, where's the min? Generally, those things are going to be given. Turn those into amplitude and phase shift and period and that kind of thing.
I had a question.
Yeah.
Is it going to be wrong if you leave the 5 or 6 outside the
would it be wrong to put the pi by 6 outside the bracket? No, I don't think so. I think that would be fine. It's a little unconventional. If you had a phase shift, it would be totally appropriate. Without a phase shift, it's fine. Yeah. You would eventually possibly get yourself into an ambiguous situation. If the x wasn't part of it, it should probably be out front. You know what I mean? Like, am I doing cos of pi divided by 6, close bracket, and then multiplying by 2? Or am I doing cos of pi divided by 6 times 2, and then closing the bracket? There is some ambiguity there, but this way I would say would be interpreted the correct way generally. Yeah. Okay, let's move on. What is the depth 2 hours from low tide? So low tide to us was time 0. So what is this saying? Oh, usually I do, it shouldn't be y, sorry, and it shouldn't be x. Let's go back and fix that. It's fine that we wrote it out that way because we were just doing it for the first time, but we usually use function notation. And so I'm going to use the variables that I defined in the graph, h at t and t, just to be a bit more consistent. So 2 hours after low tide, if it was 2 hours after high tide, then I would have to kind of use my graph to think of when that would be. High tide is 6 hours in my graph, and my graph is where the equation came from. I don't know what time of day this is, but in my graph, 2 hours after high tide is 8 hours, because high tide happens at 6 hours for me, right? But this says 2 hours after low tide. So this is saying when t is 2. Just saying when t is 2, right? So h at 2 is negative 2.8 cos of pi by 6 times 2. And so when you punch this into your calculator, you will have to be a little bit careful of brackets and such things. Plus 3.6. Try that on your calculator. Make sure you can punch it in. Again, you got to be in radians. What did you get? Who did it? 2.2? I got 2.2 as well. I like to look up and I decide, like, does that make sense? Does that, 2 hours, I mean, my graph doesn't have a scale or anything, but 2 hours after would be somewhere around there. Yeah, sure. I think that's reasonable that that's 2.2. So 2.2 feet. Watch your brackets when you do this. So something's interesting too. The way I typed it in, if you typed that in on your calculator, you would get the wrong answer. I can't show you because I can't get my actual calculator up there, but these physical calculators, unless you have an updated version and they've changed it, interpret this, the way I've written this, they interpret it as the 6 times the 2, and it's pi divided by 12, which is not what we wanted. So when I type that exact expression into my physical calculator, I get 0.9, which does not look right. That's too low to me if I look at the graph. So the better way to write it would be with a time symbol. And then I believe you should be fine, 2.2. Okay, last one. There's one more question. How many times a day is the depth exactly 6? So 6 would be here. So if I just draw a line, I can see that it's 4 times a day, right? Sometimes I like to throw in little questions like that that just make you sort of look at the graph that you've done and think about what the answer is.